Dear students, let us start discussing about generative adversarial networks and their applications in this video lecture. Before we get on to the main discussion on generative adversarial networks, we will see a little bit of motivation on why such networks are very important, like what are they for. Say, assume that we have some data samples with us. So let this be the data samples at our hand, x1 up to x1000. Okay, so these are the data samples generated from a probability distribution p of x. Okay, and this probability distribution b n 0 comma 1. Okay, see, in real situations we may have thousands of samples with us, but they may not capture all the variations of the sample space. Meaning, if we have, say for example, for a 10 face images for a 10 images for a person's face, it doesn't capture all the variations of his face. And if we have this similar problem is here. So if we have 1000 samples with us, these 1000 samples will not capture the whole possible samples that from which these samples might have come from. Say, assume that if I initially know that I have a Gaussian distribution at my hand and generate 1000 samples of this out of this Gaussian distribution, then these 10 samples speak only some information about the density function, underlying density function of the samples. But the underlying density function as such, if I can capture, then I can density of the samples, if I can capture, then I can generate as many number of samples as I need. Say for example, now the question is, the information given by p of x is much more wealth than the information given by this. So to say here what I am discussing verbally, the information content has more information, much more information. Okay, this density function has much more information than the. So now these samples need not be in one dimension all the time. These samples can be even in multi dimensions. So for example, x1 may be a sample in higher dimension. Okay, and then similarly x2 may be a sample in higher dimension, and so on. They're all 1000 samples here. Okay, please note that here what I am writing is the sample index I will write in the upper cap to be consistent with our previous video lectures. Here first sample and 1000 samples, and here x1 may have features ranging from x1, x2 and so on, xd, d features. So in this case, the probability density function what I write is p of probability density function is p of x, and this is joint density of all d dimensions. Please note the difference between the sample index and the dimension index. And what we are discussing is generative models. GAN is also a generative model. Specifically, we will be discussing on GANs, but this comes under the bigger class of models or the algorithms that tries to generate samples from few given samples. In some sense, what we are trying to do is, there is from few given samples we would like to capture the density of samples, and capturing the density of the samples we will try to generate the more and more samples which look alike like the original samples. So if we can capture p of x or p of x in higher dimensions, okay, then we will be able to generate large number of samples. Enable us generate large number of, okay, that look alike. X1 to X1000. Okay. Okay. So this is the our objective in GANs. We may capture p of x explicitly, or in some of the approaches, especially in GANs, we do not capture p of x explicitly, but still we capture the density, underlying density of the samples, so that we will be able to generate through that we will be able to generate much more samples. So we can generate from x say 1001, 2 and so on, x n, and then as infinite number of samples we can generate. That is the advantage of capturing the density, either explicitly or implicitly. Now let us go back to our discussion on like what is the motivation for these algorithms. Okay, fine. Please note that the slides in this video lecture are from Professor Fifi Lee team, and they are from CN231N Stanford lecture slides. And I would like to acknowledge both the Stanford team for the lecture slides, and as well as the respective publications where which helped us to discuss these topics better. Right. See, in as we discussed before, the GANs are mainly enablers to generate more samples that look like the given samples. But so far what we have discussed is the classification methods. So in convolutional networks, for example, we are given image, from the given image we would like to classify it as cat, dog or any other class, or given digits images we are trying to classify as 7, 8 or whatever from the handwritten digits, and so on. So here for these are all considered supervised learning methods or supervised classification methods, because we give the image as well as its corresponding label to learn the network, the mapping between the input data and the label. Essentially what we are doing in these supervised learning methods is to learn the mapping between the input data and the output label. If y equal to f of x, what we are learning is the function f, which is function of several parameters and the input. Once we give the input, through the parameters of the network or weight parameters of the network, we would like to map that input to the corresponding class label. And this supervised learning that is applied in other tasks such as object detection, semantic segmentation is also similar. In object detection, for example, we are trying to learn from the given input image where this object is located, x, y, hw locations of the object and the category of the object, class confidence of the object, or the bounding box that we consider, that is given by XYHW. Similarly, in semantic segmentation, we would like to learn for each pixel uh, what is the label corresponding to that pixel. Say for example, here is it belongs to the cat region, or the pixel belongs to cat, background green, vegetation, etc. And these are all comes under supervised learning model. Whereas the previous discussion that we had on generating more and more samples from the given samples comes under unsupervised learning, because if once we give the samples, no need to give the labels of the samples which we would like to generate. And here is usually the unsupervised methods that are very well known and widely where unsupervised learning is applied. And for example, clustering. In clustering, we try to group the samples into different categories, and here only sample features are given to us and the labels are not given, in the sense that each of these data points, for example, if I give some set of data points in 2 dimension and doesn't give the color like here red, green and blue, then what we would like to do is group all data points, or say for example, if I give feature x1 and feature x2 and make a data point out of it in 2 dimensions, based on these data points, we would like, what we do is we group the closer ones together and say that these are on class 1, the other which are apart from this and closer but yet closer within them are class 2, and so on. This is known as clustering or grouping. Similarly, even in dimensionality reduction, what we do is we no need to use the class label, especially in principal component analysis. For example, say where we consider the covariance matrix of the feature vectors or feature sample features, and identify the dominant directions of the data and project the samples onto the direction. And after projection, the grouping can be done in the similar manner that we discussed before. And this is also this is also a unsupervised learning method. The other unsupervised learning method is what we are point of discussion now, that is density estimation. Given samples x1, x2 up to x1000 or whatever, so many number of samples, we would like to get the underlying density of the samples itself, so that we can generate as many new samples as we wish to. And the difference between supervised learning, so far we have done, and unsupervised learning is, in supervised learning we are essentially doing mapping from the sample features to the output labels or classes, whereas in unsupervised learning there are no labels, and we are trying to understand the underlying structure of the data, and using that underlying structure, that is P of X in the previous discussion that we had, we would like to bring in generate more samples, or we would like to group them into different categories, or reduce the dimensions, etc. So we would like to understand the structure of the data to perform any of the applications like grouping or dimensional reduction or sample generation, etc. In literature, there are few other methods which will enable us to generate more samples. For example, this is referred to as autoencoder. These are referred to as autoencoders, which we discussed similar structure of this. This imitated by convolutional neural networks is being discussed in segmentation when we were doing image segmentation. There the input image is image pixels and the output is are labels. But here in this autoencoder configuration, what we have, input image as the image and the output is the reconstructed image. That is, we would like to just reconstruct the same image that we get in the input. Here please note that we are not using labels, but the importance of this autoencoder is, say for example, if we learn how to reproduce the given images at the output, then even if there are some missing regions or noise to the input image, that nicely suppressed or filled in by the learned network structure, and it will be able to reconstruct the image that looks more like the natural image that is used in training. So while training, if we give proper input and output, as well as even if noisy input here and pure original image here, noise free image here, then even in testing, when we give the noisy image here, it will give noise free image, or image with missing regions, small missing regions, it will be able to give the image with which looks like a real image. Say with one which is with some breaks, if we give, it will give one and the output. So that is one direct advantage of this autoencoder. Please note that this is unsupervised learning, because we are give input is anyway in our hand and we are giving the same as output. So we are not giving labels here. And what is the much more important or additional benefit of this autoencoder learning is that the features that it learns in between capture essentially the structure of the data. For example, if we have a an image which is say 256 cross 256, and through some convolution and sampling layers, if we bring the features dimensions to say 3 cross 3, then 3 cross 3 cross say 128 or channels, then these 3 cross 3 cross 128 capture most of the details of the good encoding of the original image, and thus this part is referred to as encoder. And from this 3 cross 3 cross 128 we can again get back the original image x hat, and that is this the rest of the part here is referred to as of the part of the architecture or the network is referred to as decoder. And the cost function here is x hat is to be similar to x, so it is x hat minus x whole square, that is mean square error cost function we use usually for training these things. So please note that here this autoencoder is used, can be used for generating images of, say for example, variation of this referred to as variation autoencoder is widely used for generating images that looks like neural images. So if we train with CIFAR data, 10 data, it can generate different cats, dogs and different categories that are in the input image. And as we discussed, the main importance of this is in capturing the features of the underlying data, the structure of the underlying data, and these features can be useful in image classification problems. So for example, if you want to use like exactly we do in image feature extraction methods, these features can be used for effective classification by any supervised classifier. Please note that up to feature extraction it is unsupervised. Once we use features and do apply either neural networks or SVM or any other classifier, then it is supervised framework here for classification. Also note that these features usually are lower dimension than the input image. So now let us understand how generative adversarial networks will help us to capture the generate real samples that look like the data samples that we provide as the input. As we discussed before, the important aspect that helps us to get the whole information of the input samples is the density of these samples. So if the data has x represents any data point or data sample, then p of x is p data of x is the probability density of the data. But through any model we may not be able to capture the true density, but a model density p model, if it is that is close to p data, if we are able to capture from that, if we sample, we will be able to get again large number of images. Please note that the discussion that we had before, if we have 1000 samples from n0 comma 1, and if I am able to estimate the probability density function, that is p of x, from these 1000 samples, indicating that these 1000 samples have come from n0 comma 1, then I have the whole information. I can generate any number of large and infinite number of samples from n01 that look alike in some sense to the original samples. That is the idea that is used in generative models or generative adversarial networks as well. So the advantage is we can generate large number of samples. Also in the places where we have less number of data for training, these are very useful. The other thing is in image synthesis. So for example, if I have a face which is with one say one style, hairstyle and other style, face style. Then say if I train a network with different images, then then I will be able to generate for a test image any other new styles and new face images. So if I train with say digit images, so the network will be able to generate, or the model will be able to generate new character images, handwritten character images that look alike the original previous character digit images. And it can also be used for some of the applications like coloring, sketches, etc. So based on the training, it has lot like the more way we train the network, it's it has applications in image synthesis, and generating the more and more images, and generating different category of images, and generating one image to another image and so on. And usually generative models are of different nature, based on whether they explicitly estimate the density or implicitly estimate the density and generate the samples directly. So the GANs comes under directly generating the samples, where it implicitly understands the density and explicitly generates the samples, whereas the other models explicitly generate the density as well. But the samples that are generated from GANs are much more realistic than the samples that are generated through the other methods we have so far. One example of the method that explicitly generate the density is this. So this is say what we are trying to capture is given previous pixel information in an image, we would like to say what the current pixel is. Say for example, if we formulate the probability of current pixel, in pixel means the intensity of current pixel, as the function of previous likelihood of other pixels. So if whichever the likelihood is maximized, that will be the correct pixel at that location. So here, say for example, if you want to predict the pixel here, so then what we use is we use its neighbors. So three of the neighbors here. So for example, for any pixel here, m minus f of say I of m comma n, I of m minus 1 comma n, I of m comma n minus 1 will be its previous pixels. In fact, I of m minus 1 comma n minus 1, or any pixels with say m minus and n minus are previous pixels. So we use the previous pixels to generate the current pixel, or we define the likelihood of current pixel with respect to the previous pixels, and whichever the possible value that maximizes the possible value for x that maximizes the probability p of x given xk minus xk given xk minus 1 xk minus k minus 2 etc. will be the correct highest probable one will be the correct pixel at that location. This kind of prediction of current pixel p of xk given xk minus 1 xk minus 2 and so on can be done by RNN or by a CNN as well, convolution neural networks. Since we know better convolution neural networks now, by now, so the prediction of this pixel which is in black can be done by neighborhood pixels here, which are in past, and these are all given as different input. All these pixels in one dimension form will be given as input to a one dimensional convolution neural network, and the output probabilities are for each of the digits, like this black value taking 0, 1 and up to 255. These probabilities are the outputs given by the convolution neural network, and these probabilities will help us to assess which is the most probable pixel at that location. And this probability density is captured once the training is done for a particular class of images, and this is referred to as pixel CNN. This also helps us to generate good samples of natural images like CIFAR10 or ImageNet data, but these are quite still not as good as the natural images that we get. And GANs will help us to generate much more better images. And one more, the important limitation of this kind of image or pixel generation is that we can generate pixel by pixel only, and this is a sequential way of generating the images. and usually it is very time taking because image of high dimension, and generating image at a stretch gives us a good reduction in terms of in terms of the time with which we can generate the more and more images or samples. Now let us start come to the discussion on what generative adversarial networks are. See, in this generative adversarial networks, rather than like previous methods that we have discussed so far, where we have a classifier and we give the input at the beginning in at the input data sample at the one end and the label at the other end, we directly back propagate the error here to adjust the weights to map the say x to y, x being the input and f of x being output, that is mapped to y. Here these in these generative adversarial networks, one network assume that the generator networks generates an image. This image usually is fake because the generator networks usually is initialized with random weights and random variables, random weights and kernels. Once we generate randomly, it gives usually a absurd result or spurious results, and this may not agree with the real example that we have. So the question is, if this generator networks generate some fake samples, how another network, a discriminator, which looks at the ground truth, can tell whether they are fake or not, or rather the discriminator network which will look at these real samples need to say that they are fake. So the idea is generator networks generates fake samples, and the discriminator generator networks takes some raw input or even noisy spurious input or noisy input, and then generate some fake samples, and these samples are to be shown to the discriminator, and discriminator also sees the real sample and it says that it is fake sample. So it's like a detective which looks at a particular thing and then it also knows say how the real thing should have been and says that it is fake. And this discriminator is like a cryptic which says that say for real sample x the probability is 1, and for generated fake sample the probability is 0. And now let us see how this discriminator since we know here discriminator knows here the real sample and assesses the fake sample, this discriminator weights or the kernel can be adjusted, and then these in turn will the generator adjusts itself to satisfy the discriminator in some sense. Say that means discriminator will not be able to detect later that the generated sample is fake sample, or in other words the generator generates real samples almost real looking samples such that the discriminator will not be able to distinguish whether the generated sample is fake or not, even after looking at the real and fake samples together. They look alike, so it will not be able to tell. So that is the situation generator want to create for discriminator, and while the discriminator also mainly tries to say that the generated sample is fake by the generator and it has the real sample and it learns the what is real sample. So here discriminator has two objective functions. So let us see how the cost function in this case like in GANs we can frame. So let us discuss on the cost function which is optimal for this generative adversarial networks. So as we discussed before, okay, so let us assume that we have some input here. This input may be some random distribution even. So in fact GANs can generate uniform distribution to Gaussian distribution, and even from uniform distribution samples. Say for example, if I generate say 1024 cross 1 samples or 102, so these are all say from n0 comma 1 for example, this can be given to a generator. This is this number is just written, but I think this this is not this in general can be anything, and once we give the real some uh, some noise to generator. This generator job is to generate samples which look like real samples, but this generator is a convolution neural network usually here, because with the best functions, that function mapping that we can do is through convolution neural networks. So I assume that we have a convolution neural network where it has series of upsampling layers, and finally comes like, say for example, this is 32 cross 32 or something like that. Okay, so it is either images of some dimension. So let it be 32 cross 32. Okay, with 3 channels, so it is 32 cross 32 cross. Okay, let it be some image, it is generated. Okay, and as we discussed before, the job of discriminator here, discriminator is again a neural network. The job of discriminator is takes this input from the generator, and this is said to be fake. So usually we start with random initialization, so it will be very noisy, and thus the discriminator main job is to say that it is fake. And then the real sample also it looks at, let x be the real sample. Then the discriminator job is to say x is, say the d of x is its output, d of x to 1. Okay, so discriminator usually has sigmoid activation or the softmax layer at the end, and hence it is a classifier network in some sense. And this is usually either autoencoder kind of thing, or some network which will have a output neurons of 2 dimensions, 2-dimensional output neurons, and generates an image here, and this is a real image. Okay, and discriminator has a gives a probability for x, that is 1, and discriminator also gives probability for fake sample, okay, that as 0 it has to give. Okay, so given that, what discriminator is trying to do is 2 multiple jobs. One job is, say, probability of true, so true sample, say for x being true sample, p of is equal to 1, and probability of discriminator in this case is d of x. Okay, and probability of 1 minus p of d, sorry, so, and similarly, so the job of discriminator here is to say that if the true sample, for true sample it is 1. So based on cross entropy loss, so if we write one term of the cross entropy loss, what we get for discriminator is probability of discriminator here, okay, or the loss function corresponding to the discriminator, one into ln of, assuming that cross entropy, ln of d of x, okay, plus 0 into ln of 1 minus of d of x. Okay, this is the cross entropy loss. P of, say I write the probability to be optimized, so probability function to be optimized by discriminator. So I write here, so it is not loss, but as such we would like to maximize the objective function. Okay, so this is the cos function of discriminator, or objective function of discriminator. Okay, so and then this, what we want to do, we want to maximize with respect to parameters of discriminator. Okay, because assume that d is a discriminator is a neural network which having its kernels and weight vectors as parameters. But there is another job of discriminator, that it has to say that the sample generated by, it also has to say that p of t is equal to 0, okay, for g of z, okay. So it has to say that the ground truth is, or probability of detection has to be g of d of g of z, sorry, it has to say that p of t equal to 0 for g of z, or p of, sorry, d of, that is discriminator. So if I pass g of z through discriminator, what I get, the probability, estimated probability of by the discriminator has to be 0, okay. So how do I say that d of g of z is equal to 0 has to be mapped to 0, okay. So how do I map this to 0? This is the fake sample, okay, and discriminator has to map fake sample probability to 0, okay. This is its objective. Another objective, the discriminator has dual objectives. One objective is to map, this is what is this objective that it is doing, the real sample, okay. And what is the objective of this discriminator here? It is trying to say that probability of real sample, okay. D gives the probability, please note that, has to be mapped to 1, okay. This is one objective and this is another objective for the discriminator. Given these two objectives, now, so I am writing PT only for this particular instance. So given this, now how do I write? JD2, the other objective of this discriminator is ln of d of g of z into 0 plus 1 into ln of 1 minus of d of g of z, right? Okay. So now bringing both together, the objective of the discriminator is this. Please note that here this term is 0 and here this term is 0. The total cost function of the discriminator is, or the objective function of the discriminator is ln of d of x plus ln of 1 minus d of g of z, okay. That means the discriminator tried to say that real sample is real and fake sample is fake, okay. The probability of fake sample should be close to 0, whereas the probability of real sample has to be close to 1. That's what the discriminator is trying to say. So what we should do with this cost function, discriminator has to be maximized for this cost function, okay. So what we want to do, the discriminator adjusts such that, so you find theta hat such that maximize with respect to d of theta. D of theta means parameters of theta. They may be kernel weights, kernels or weights. Usually it has a set of convolution layers followed by fully connected layers as well in some cases. So ln of d of x plus ln of 1 minus d of g of z. Please note that this is the probability of fake sample. D of G of Z is probability of fake sample, and so simultaneously maximizing probability of real sample and minimizing the probability of fake sample. Whereas, what is the role of generator now? This is all regarding the discriminator. Net. Okay, and the discriminator, and then this is for generator. Okay, role of generator. What generator has to say? Generator has to say that whatever it generates, G of Z is okay, is correct. Has to say that it is look like real, and to say that what it should do, it has to maximize D of G of Z has to be 1. Okay, so how do I do this now? The objective function for generator is ln of D of G of Z has into 1 plus anyway other thing 0 into ln of 1 minus D of G of Z. Okay, so this has to be maximized with respect to G of theta. Okay, so this is the objective of generator. So what we can write is the generator objective is find theta hat such that this theta is generator theta. Please note that generator also is a CNN that has kernels, and now the objective is to either maximize this or minimize. I am just writing a dual cost function. Can you guess why I am writing dual cost function here? ln of 1 minus D of G of Z. And thus, why do we have written dual cost function? Because please note that the cost function in the discriminator already has this term. I would like to bring this term in the similar fashion, so I have written the dual cost, another version of the same cost function. So now the overall objective of GANs is minimize with respect to parameters of the generator and maximize with respect to parameters of the discriminator the cos ln of D of x plus ln of 1 minus D of G of Z. Okay, this is the objective that the GANs try to optimize, and this can be done either directly like this, maximizing once with respect to discriminator. Once it maximizes these parameters of the discriminator, then it again tries to check with respect to generator and it is its parameters. Okay, or this can also be done both as maximization problems where the cost function given by this is maximized for discriminator, cost function given by this is maximized for generator. This is ln of D of G of Z. Okay, right. So usually people prefer to do both maximizations for stable convergences. Let us go back to our previous discussion. Right. So here you can see that the generative adversarial networks has two networks. One network is attempting to generate samples that look like real samples, and the other network looks the generated samples as fake samples. Comparing with the real samples, it adjusts itself to say how fake they are fake. And then the generator tries to adjust itself from the indirect feedback that is given by the discriminator to generate more real looking samples. After the convergence, the generator generates real samples, all samples that look like real samples, and discriminator will not be able to distinguish whether the sample generated by the generator and real samples are different. Okay, so as discussed before, this is the cost function that we have discussed, that is optimized in GANs. Please note that there is also an expectation term here, which we need to consider, because if we consider one sample, then what is the cost function we have written is this. But if we have more and more samples, then this is the expected, there will be expectation x is taken from, it has to minimize over large number of samples, real samples, that is p of x. So this is from data distribution, and this is z has come from model. X. Okay, so let me write this little clearly. Z model of Z. Okay, so this is the model. So what we are trying to say is, we generate so many we take many samples, real samples, from the data distribution. We generate noise vectors or noise samples and give it as input to the network from the noise distribution. Okay, so please note that the expectation need to be there everywhere, considering that we usually, for optimization, we take large number of samples, not just a single sample. Okay, so expectation has to be there everywhere. Yeah, I leave it here. Please note that the expectation is there. The optimization is done over large number of samples. Yeah. So as discussed before, the optimization can be done both as maximization problems or a min-max objective function. And usually min-max both maximizing different objective functions in both for respect to objective functions is more stable. Since we have two networks here, and the networks are not given direct say input output back propagation, the training and convergence of GANs is more challenging, and hence there are several methods that are proposed for improving the training of the generative adversarial networks. Still, it's a good challenging problem, open problem, to make them converge very well in many situations, in some difficult situations at least. Yeah. So the here you can see a algorithmic steps for training this generator, discriminator, and the generator. Usually we first train the parameters, we adjust the parameters of the discriminator to maximize the cost function, and then followed by the adjusting the parameters of the generator that fits to the discriminator parameters, and says will try to generate real samples, real looking samples, or indistinguishable samples for the discriminator. And here you can see the discussion that we had, and here are the samples that are generated from the GANs. So you can see here the generated samples almost look like original samples, and the nearest neighbors are from the data set, real data set, and this if you see, they are almost indistinguishable, and they generate slightly different samples that are not there in original data set. And compared to the other methods, these generate much better samples. While training GANs, as we discussed, there are few important aspects to consider are usually we use the batch normalization in training, and for upsampling from lower dimensional noise samples to images in generator, we apply standard convolution and use ReLU and leaky ReLU in generator and discriminator. And these are you can see some of the real looking samples generated by GANs. As you can see, generating such samples of natural images is almost like a great job that recent convolution networks or GANs were able to do. These have different other features. So for example, the GAN based features can enable us, or learning can enable us to dissect to make editing at the feature level. So now if we have, for example, some of the persons with glasses and some of the images, so we can take the features of this person and we can embed the features, subtract from this, and then add the features of another person, and then it looks like as if the other person is wearing glasses. So now you can do almost like image editing in feature space and get much real looking like edited samples. So it can also be used for several other image generations, like so it can generate say one image to another image, and so on. And there are plenty of methods that evolved based on this application of GANs, and as well as for making convergence, for suggesting better training methods for convergence of these GANs. Usually DC GAN is one of the well-known standard architecture for this implementation of GANs for images, where you have actually deep convolution networks as the generator and discriminator. And these are like some of the images that are generated from GANs. And as discussed, for convergence, people have suggested different cost functions rather than what an improvement to what we have discussed in the previous discussion. And those are actually versatile GAN, progressive GAN, etc. This gives different slightly different flavor of the cost functions to better converge and all. As we discussed, these are all useful for synthesis of the different kind of images, as well as from sketches to the coloring, etc. So as so this is the summary of the generative adversarial networks. These doesn't explicitly capture the density, but generate samples that are much more realistic than many of the previous methods, and these are useful in generating samples where there is a scarcity of samples for training, and also to generate samples which look like real samples, and can augment the data sets that we have. Also to generate samples that say different styles and different versions of the original images. So we will see few of the other important applications of GANs in the next video lecture. Thank you.